Welcome to the Enamena video tutorial about concentrating solar power. This session is about central receiver systems. To introduce myself, my name is Marek Röger, and I got my PhD at the University of Stuttgart in mechanical engineering, and I've been working in the CSP field over 13 years, both in central receiver systems and in parabolic troughs. What are the different components of a solar tower plant? Well, at first we have got the solar field, which you can see here. This solar field reflects sunlight on top of a tower. On the top, a receiver is mounted, and this receiver absorbs the radiation, collects the heat. Then, usually you have a heat storage and a conventional power block, which you can see here. Let's go into detail into the different components of a solar tower plant now. I want to point out here that the heliostat costs constitute more or less half of the costs of a solar tower plant. Hence, a reduction of these heliostat field costs, or the use of fewer heliostats because of a better efficiency, directly reduces the levelized electricity costs. The heliostat field is quite important, and the following chapter is giving some details on this field. Let's start with the individual heliostat. Here as an example, a T-type configuration. This heliostat normally has got a foundation. It has got a structure consisting of a pedestal and an elevation axis, which is perpendicular to the pedestal, and the back structure. Then we have got a gearbox and the facets which are mounted on the back structure. Usually, the facets are held by 3 points in order to adjust the orientation of the facet. From the cost side, the drive is about half of the costs of a T-type heliostat. So, if you want to reduce costs, the drive is an important factor. Here I want to show different examples. There are a variety of different heliostats which can be clustered by size, by type of facets, by the type of kinematics and type of the drive. So here, 2 examples of large area heliostats are shown. This is the Senair on the left-hand side and the Abengoa Solar on the right-hand side heliostat. These are large area heliostats. That means you could put a tennis court on this surface, and this tennis court has to be moved correctly over the whole day. Also, there are other concepts. These heliostats consist of glass facets, while these heliostats here consist of pre-stretched membrane technique. That means you have got a pre-stretched metal membrane on which thin glass mirrors are glued and a can which is evacuated, and the pre-stretched membrane then gets this ideal shape by the pressure difference. These heliostats are also large area heliostats. The Steinmüller heliostat measures 150 square meters. The Syke heliostat measures 170 square meters. It is not yet clear if the reduction of costs is achieved by using fewer parts, which have to bear higher loads, that would mean large area heliostats, or using a lot more parts, which have to bear lower loads and are much easier to handle. That means if we should use smaller heliostats. So other companies go for small or medium area heliostats. For example, eSolar use facets of a surface of about 1 square meter only. You see here a worker mounting this heliostat without any crane. Or also there exist concepts like the hydrohelio heliostat on the bottom, which use, for example, hydraulic drives in order to track the heliostat. So there's quite a variety of different heliostats, and to repeat, we can distinguish either the circular stretched membrane heliostat with thin glass mirrors. The example would be the Steinmüller or the Syke heliostat, here shown here. The way the heliostat is mounted, so we can distinguish the carousel type, which would be the Steinmüller concept, from a pedestal-mounted T-type heliostat, the other ones. And we can distinguish the type of drive, the hydraulic drive or a gear drive. There are other concepts which still have to be proved if they are cost efficient. So for example, you could connect individual facets by one motor, and then you would have a heliostat with ganged facets. So we would save in terms of motors and drives. Also, a target-aligned heliostat exists. That means that the rotation axis, one axis, is aligned to the receiver, and the other axis is perpendicular to that axis. These heliostats tend to have a high quality because they have got low astigmatism errors. However, they are not so cost efficient in terms of construction. And last but not least, there are concepts still in research and development, like for example the concept of the Solar Institute Jülich. They try to reduce wind forces by using a stationary segment or stationary box, here shown on the right, with inlying tracked micromirrors. Important issues are the shape and the deviation from the ideal paraboloidal shape, because this influences the ability to focus light onto the receiver. The shape is not ideal because there are different sources of errors. You can think over contour errors. These contour errors are usually caused by gravitational forces and moments, by wind forces and moments, by canting error, and by temperature difference. So here we made one example of an heliostat facing to the zenith, and we measured the shape of this heliostat and compared the shape with the heliostat facing to the horizon. If we compare the two shapes, we get this plot here. Blue means we have no deviation, and red means we have got a high deviation. And if you have a look on this heliostat on the right top and on this plot here, you see that between the two extreme positions, the heliostat moves. So we have on the edges up to 5 millimeters deviations. Also, we can examine or study a heliostat by finite element analysis. This is the picture shown here. Also, the shape is influenced by wind forces or even the way we put the facets on the back structure. So this is called the so-called canting error. Also, temperature differences may cause a change in the shape of a heliostat. Also, the optical performance of a heliostat is influenced by the tracking of the heliostats, and we may have tracking errors. So we may have misaligned axis. That means that the pedestal is not perpendicular to the elevation axis. We may have a drive backlash. The wind forces may influence the tracking accuracy, and we have discontinuous tracking. Discontinuous tracking means that the heliostat is not tracking the sun constantly, but with time intervals of 3 to 4 seconds. Last but not least, we have got a mirror waviness in the scale from centimeters to meters, and we may have mirror roughness in the scale of sub-millimeters. There are different measurement techniques to measure, for example, mirror waviness and the contour errors, like the deflectometric measurement, which is topic of another session, or the flux measurement in order to check the tracking and the canting. Now, let's come to the question how we have to arrange the heliostats to come to a proper heliostat field. That means the heliostat field layout. The different loss mechanisms are shown on this slide. At first, the heliostat field density should be as high as possible, so that the distance to the tower is minimal, because we have got atmospheric attenuation, we have got the influence of contour and tracking errors and sun shape. And the farther a heliostat is away from the tower, the more pronounced are these effects. On the other hand, a dense field leads to blocking and shading. On the right photo, here on the bottom, you see blocking. Blocking means that sunlight reflected off a heliostat is blocked by the heliostat row in front of this row. Also, cosine losses exist. This means that the receiver does not see the whole mirror surface, but a projection of this surface, which is smaller. And last but not least, we have got the mirror reflectivity, but also the specularity of the reflection, which is important regarding the beam spread. This slide shows the different heliostat field layouts. For example, here in this photo we see a north field, like in Spain at the Plataforma Solar de Almería. Usually this kind of field is used in high latitudes, like in Spain, and typical receiver types are cavity receivers or external north-facing receivers. For the southern hemispheres, you should replace north by south. If we go further to the equator, the north or south fields get bigger and we get usually surround fields. Also, if you want to use external surround receivers or facing down receivers, usually we have got surround fields. And last but not least, we have got special field configurations for special receivers which use secondary concentrators. So here on the bottom you see a single eye concept, you see a cluster of receivers with secondary concentrators, and you see a kind of ellipse on the ground, which is the field. But you can also think of a multi-eye concept where you've got multi-eyes and then you have got a field consisting of subfields. There exist different layout softwares which optimize the individual heliostat positions, the tower height, and the orientation of the receiver. Some of them are listed here, for example, HFL-Cal, DAL-Sol, RSOL. More exist on the market. We can also have different tower configurations. For example, a single tower, like here at PSA, or you can think of multi-towers, or even multi-tower solar arrays. Multi-towers are several towers which use the same power block. Multi-tower solar arrays means that heliostats may use different towers depending on the sun angle. This is especially interesting if we have less surface available, for example, in urban areas. And you can think of a beam-down concept. Here, a sun ray is reflected on the heliostat field and is reflected on a secondary concentrator, which is on top of a tower, back to the ground. This configuration has the advantage that the receiver and the power block, or even chemical blend, can be at ground level. But mostly you need a third concentrator here on the bottom to reconcentrate the light. This picture shows the beam-down concept at the Weizmann Institute of Science. The photo on the left is a view from the receiver up to the concentrator at the tower top. In the concentrator, here you see the heliostat field, which reflects the sunlight into the receiver. So what we see is the top reflector, and in the top reflector we see the heliostat field. You also see the wall of the third concentrator. A challenge of this concept is the more or less large top reflector, which has to withstand wind forces and maintain a good optical quality. And due to a further reflection of sunlight, there are higher reflection losses of the optical systems than for a classical non-beam-down concept. Now let's come to the next section. We have got the tower, and on top of the tower we've got the receiver. Towers are usually normal steel constructions, concrete constructions, or even wind turbine monopoles. There are different receiver configurations. They can be divided in two basic configurations. Here you see an external receiver. It has got a simple construction, but a high acceptance angle, because light can be intercepted from all the sides, but it has got also high losses, because convective losses are pronounced and also radiation losses are pronounced. Another concept is the cavity receiver, where the losses are reduced. In a cavity receiver, we have got a small aperture, and the receiver panel is lying in the back of this aperture inside a cavity. Radiation is reduced and also convection. But the acceptance angle is smaller. That means radiation from the side, for example, cannot enter the cavity and cannot be used. Before I go into details of the different receiver tech designs, I want to present the different physical concepts which are used in the receivers. As first example, we have got a tubular receiver. That means we have got a simple tube, shown here on the right-hand side. We have got solar radiation impinging on the tube. And inside the tube, we have got a medium. This medium can be molten salt, molten metal, could be water, steam, or pressurized air. The tube wall is a heat resistance, so we have got a temperature difference over the wall thickness. That means that the outer tube wall is always hotter than the medium inside the tube. This means we have got radiation to the ambient, which may be higher than in other concepts. It is also beneficial to have a fluid with good convective heat transfer properties, for example, molten salt or even liquid metals to lower the tube temperature, because this reduces thermal radiation and increases receiver lifetime. A second option is to use so-called volumetric absorbers. In a volumetric absorber, the solar radiation is absorbed in the volume. So solar radiation enters into this volumetric matrix. Also, the heat is transferred in the volume. Especially used with air as working medium, the high surface of the volume compensates for the fair heat transfer characteristic of air. The cold air enters at the absorber from the front side, cooling it down. The volumetric effect is the fact that the irradiated front surface of the absorber is cooler than the internal section of the absorber. This is shown in this diagram. Here, the material in the front side has got a lower temperature than the medium on the outlet. This lowers thermal radiation losses and is beneficial for the material. There is a third option. It is also possible to irradiate directly a receiver working medium which is flowing through the receiver. That means solar radiation is focused on a moving bed of particles, for example, or even a moving molten salt film, and this film is heated while it is moved through the focal region. These are the so-called direct absorption receivers, DAR. The advantage is that we don't have any wall and no extra volumetric structure. We may use the working medium directly as storage medium. We may use the working medium directly as storage medium. Let's come to the first example of a volumetric air receiver. This is a quite simple receiver concept because we use air as working medium under atmospheric pressure. This is the PHOEBUS-Concept, and ambient air is heated by flowing through a metallic wire mesh in the receiver. The hot air then flows either through a thermal storage here or through a steam generator, generating steam at 480 degrees C and 26 bars. The air leaving the steam generator is still over ambient temperature and is recirculated in front of the receiver. Part of this recirculated air is taken in by the absorber, another part is lost. The amount of recirculation strongly depends on the wind conditions and receiver design. This technology was successfully tested during the TSA program in Spain at the PSA. Different volumetric structures can be used as receivers. Here you see some examples. You can think of metallic or ceramic meshes. You can think of metallic parallel channel structures, or even ceramic parallel structures shown here. Or you can think of ceramic foams. The open porosity is usually between 50 and 98%. High open porosities minimize the directly irradiated front surface and hence lead to lower front temperatures and heat losses. What is an ideal volumetric absorber? An ideal volumetric absorber should have a high absorptivity. That means it should be a black. It should have a low extinction coefficient. That means it should have the volumetric effect. We want to have a high open porosity and good heat transfer characteristics. That means we want to have a large surface for the heat transfer medium air. We want to have a high temperature stability, no mass flow rate instabilities between different regions, a long durability, and the material should be economic. After the successful TSA program, which was the PHOEBUS-Concept, which used a metallic wire mesh as absorber, a series of research and development programs using ceramic absorbers was launched. One of the most recent R&D programs was the Solar Air Cosmocell project tested at PSA. Small ceramic cups are used there. You see them on the right-hand side, 3 cups. Solar radiation here in this sketch is coming from the top. cold air enters these ceramic cups and is sucked through the absorber, and it is heated up to temperatures of 760 degrees or even 1000 degrees C. The recirculated air also serves as coolant for the metallic back structure here. These individual cups, the receiver is composed of several of these cups. So the receiver cup is the smallest unit. In this project, it is silicium carbide, which withstands temperatures of about 1400 degrees Celsius. And they have the volumetric effect I told before. So one cup yields to a sub-panel, and this sub-panel is mounted to a small receiver panel, which was tested at PSA. And 64 times this small receiver panel yields to a surround receiver of 192 megawatt thermal power. This type of receiver is used in the solar tower Jülich in Germany. You see here the solar field and the solar tower. Also, solar radiation is not abundant. The solar tower Jülich serves as technology demonstration and research platform. It has got over 2,000 heliostats of 8 square meters each, and the turbine power is about 1.5 megawatt electric. Another technology regarding receivers are the so-called molten salt receivers or salt-in-tube receivers. Let me present you the system. Usually you have got a cold and a hot storage tank. Salt from the cold storage tank is taken. So cold salt is taken out of the cold salt storage tank and flows through the receiver. It is heated up to 565 degrees C and stored in the hot tank. The salt usually is a neoeutectic mixture of 60% sodium nitrate and 40% potassium nitrate. The advantage is that the receiver working medium and storage medium is the same and no heat exchanger is necessary between working and storage medium. Electricity production can take place using the heat of the thermal storage also at night. In the 90s, there was a demo plant in the United States, the so-called Solar 2 plant, which was operated successfully. And nowadays, the newest plant with this technology is the Gema Solar plant in Spain of the Torresol company, which has 20 megawatts electric power and is in operation. The achievements in the Solar 2 projects is the validation of the design, performance and operation of large-scale molten salt receiver systems. It was shown that the thermal energy storage is possible and that the operation 24 hours a day, 7 days a week is possible. But also, there are some lessons learned. For example, the salt should not have a lot of impurities because in the Solar 2 project, first NO2 evolved while heating the salt. Also, regarding the tubing, we have to account for proper heat tracing. We should reduce the number of valves. Maybe don't use ball valves, but gate valves, and use the self-drainage of tubes. Stress-assisted intercorneal corrosion with moisture was observed. So we should use high alloy stainless steel or avoid moisture. And they showed that high solar fluxes up to 1.5 megawatt per square meters are possible. Another type of receiver are the so-called steam receivers. Let's give me some examples. Steam receivers are receivers which directly produce either saturated or superheated steam. And some superheated steam receivers of the history are, for example, the Solar 1 receiver in the 80s in the United States, or the CSA 1 receiver in Spain at the Plataforma Solar de Almería in the 80s. Nowadays, companies develop superheated steam receivers, for example, Bright Source with superheating up to 550 degrees C with reheat. In Aventpar, California, 3 plants are being built, totaling 392 megawatt electric. The eSolar project is already in operation. It's a 5 megawatt solar tower. And we have got the saturated steam receivers, which are in operation. They are built as the first solar towers in Europe by Abengoa Solar, the PS10 and PS20 plants. There are some important issues connected with steam receivers, which which people learned during the first projects. So we have to use high pressure tubes with thick walls. Steel alloys must cope with high gradients and fast transients. Evaporator and superheater section should be physically separated, and the startup process has to be elaborated. On the left you see an image of a Solar 1 receiver. This receiver was a 31 megawatt thermal receiver. It was a single pass to superheater receiver, and the peak fluxes achieved were about 300 kilowatt per square meter. Another receiver technology which is still under research is a so-called pressurized volumetric air receiver. Why do we need a solar tower and a pressurized air receiver? We have learned in previous sections that solar towers deliver high concentrations and hence can deliver high temperatures with a high efficiencies. And hence we can use a combined cycle with a high total system efficiency. Also, we are allowed to use hybridization because fossil fuels are used with high thermal efficiency and less cooling water is needed compared to Rankine cycles. But if we want to use gas turbines, we have to work with pressurized gas as a medium, so we have to use special receivers. Here's a sketch of the type of system. So the heliostat field collects the light. A gas turbine compressor compresses ambient air. Then the pressurized air is led to the receiver, heated up. The gas can be heated up further by a gas burner and then is used in a turbine section and the generator to produce electricity. The waste heat usually is used in a bottoming steam cycle, and we can use this heat in a steam turbine and hence can achieve high total efficiencies. The concept uses several smaller receiver modules which are connected either in series or in parallel. Low temperature modules can be of a simpler technology and can be built with cheaper materials than high temperature modules. So a cluster of these modules, here with the 3 modules, here you see more of them, should be arranged in a way. In low solar flux zones, low temperature modules are used. That is here in the borders, we have low temperature modules, and in the high solar flux zones in the center, we should use high temperature modules. High temperature modules go up to 1000 or even 1100 degrees Celsius, while low temperature modules go up to 550 degrees C. A low temperature module still can be realized by a tubular receiver. A thorough design must be made in order to achieve a low pressure drop, which would be harmful for gas turbine efficiency, low receiver tube temperatures, and thus high receiver lifetime. Also, compensation of thermal expansion must be considered. The module shown here was successfully tested at PSA with overall efficiencies of about 80% and temperatures up to 500 and 550 degrees C. For the middle and the high temperature module, another technology must be used. The middle and high temperature module basically consists of an internally isolated pressure vessel, which is shown here, closed by a fused silica window, which is shown here. Solar radiation transmits first the secondary concentrator, which reconcentrates solar radiation through the aperture, then transmits the window and is absorbed in the back-lying absorber here. Pressurized cold air is coming through the air inlet and is heated while passing the absorber. The window is necessary because the air is pressurized. Here you see this quartz glass window mounted on a metallic flange. And in the back you see the pressure vessel and the volumetric absorber structure. The fused silica window is highly transparent for solar radiation, but only partly transparent for thermal radiation. Solar radiation transmits well, while thermal emission of the absorber to ambient is reduced. We see this in these 2 plots. In the bottom you see the solar spectrum, blue here, and on the top you see the blue line, the transmittance of the fused silica window. And you see that the solar spectrum transmits through the silica window. However, for a 1000 degrees C spectrum, this is the green line, you see that only a part, the part which is below 3.5 microns, transmits the window, and the other part on the right-hand side is absorbed in the window. That means it is kept in the system. Also, the window reduces convective losses, and the window is formed like a dome because this shape enhances transmittance of sunlight and bears the pressure load of the receiver. Sound engineering must be used to bear the window on a water-cooled window flange. The problem of movement due to differential thermal expansion between metal and fused silica was solved. The forces on the window are huge, over 30 tons weight for a pressure of 15 bar. For outer temperatures over 850 degrees C, we have to use an active window cooling. As the window only can be built up to a maximum diameter, but the pressure vessel is larger, a secondary concentrator is needed to cover the whole irradiated area. In order to cluster the modules, a hexagon secondary inlet aperture is used. Here you see a photograph from the inlet side and you see the hexagon, and here you see an image of the secondary concentrator from the side. Here you see the outlet aperture, which has got 18 edges. A secondary has always got a limited acceptance angle, as shown on this graph. That means, depending on the incidence angle of the light, for lower incidence angles we have got high transmission of light. The light goes through the secondary concentrator without reflection and without absorption. But for higher angles, we see that the transmission goes down and the reflection increases. So we have got a limited acceptance angle for a secondary concentrator. Due to this limited acceptance angle, the heliostat field has to be designed accordingly. So you see here an ellipse of heliostats, which are quite good in order to be used in connection with a secondary concentrator. The plots on the right show efficiency maps for heliostats. We observe that heliostats far away from the optical axis have a lower efficiency, for example heliostats in the back or on the sides, and in the optical axis we have got heliostats with good efficiencies. Also, we see here the evolution of the secondary technology. We see here an older secondary concentrator and here a newer design. And we see the new design has got a higher region with good efficiencies than the older design. In the reverse Solgate project, a pilot system comprising low, middle and high temperature module was built at PSA in Spain. Here you see a schematic drawing, and you see here the small gas turbine. Cold pressurized gas is then led to the low temperature module, from the low temperature module to the middle temperature module, and then to the high temperature module, where it is heated up to 1000 degrees C. Then this high temperature gas is led back to the gas turbine, where the energy then this hot gas is led to the gas turbine, and finally the generator is driven by the gas turbine. The system was tested successfully with having some hundreds of hours of operation accumulated. Outlet temperatures up to 1030 degrees C were achieved with absorbed solar powers of about 750 kilowatt thermal and a gas turbine output of about 230 kilowatt electrical. The system was quite well controllable and the efficiency was quite good with about 80% receiver efficiency. The total system efficiency was about 20%. This is not perfect because the gas turbine was a helicopter gas turbine and was not optimized for high efficiencies. Let's come to another type of receivers, the so-called direct absorption receivers, in particular particle receivers. These receivers are still under research. Direct absorption receivers absorb the heat directly in the receiver working medium, which preferably is also used as storage medium. The falling particle receiver is a special type of direct absorption receiver. The particle curtain absorbs the solar radiation. The mass flow rate can be adapted according to the incident solar radiation. So here on the left we see a photo of operation with low mass flow rate. However, we see here a low mass flow rate also means a low absorptance of the curtain and hence a low efficiency. While on the right-hand side you see a test with high mass flow rates for higher irradiations. Recirculation of particles, for example, can improve the efficiency in part load. Here in this picture, you see a top hopper with the small particles. These are around 0.7 millimeters, and usually they are of aluminum oxide doped with blackened the particles. Also, particle velocity increases with particle fall length as particles accelerate in free fall. Here the position below discharge, and here the particle velocity, how it increases. Both simulations and measurement are in good agreement. This leads to the fact that we have lower opacities or absorptance of the curtain with higher distance to the discharge position. This is the right figure. Also, a dependence of opacity on mass flow rate is shown. The advantages of a direct absorption receivers. They directly absorb the solar radiation in the receiver working medium. The receiver working medium mostly can be used as storage medium. So high solar fluxes are possible, and we have got a low sensitivity to peaks and transients in solar radiation. We don't use expensive high temperature alloys. The receiver works at atmospheric pressure. And we can operate continuously high temperature processes, for example, for electricity generation, to drive supercritical steam cycles, or Brayton cycles, even closed Brayton cycles. Or we can use in thermochemical processes, for example, hydrogen. There are still a lot of challenges which have to be tackled for the particle receivers. For example, for the receiver, the susceptibility to wind and particle loss, the issue of part load behavior, and the thermal loss by convection. One concept to overcome the challenges regarding the receiver is to use a face-down configuration and a surround heliostat field. One concept to overcome the challenges regarding the receiver is to use a face-down configuration and a surround heliostat field. Better part load behavior could be achieved by recirculating of particles. But also, attrition and sintering of particles must be tackled and could be solved by particle engineering. And particle heat exchanger is an issue. We have to get out the heat of the particle to our working medium, for example, our steam or gas for the gas turbine. So we can use direct contact heat transfer, for example, to air, or tubular heat exchanger. After a direct contact heat transfer, the air must be cleaned from dust due to the attrition, and a tubular heat exchanger must be designed properly to not lose its temperature stability due to wear by particles. Some other DAR concepts are shown here. For example, we can imagine a fluidized bed particle receiver where the particles are fluidized in a gas. Also in literature we found submicron absorbing particles in a gas flow where the black gas acts as a selective absorber, or we found concepts of melting particle receivers. Here on the right-hand side, there's a concept of a molten salt film direct absorption receiver. That is, we have got a molten salt film which is irradiated from the field and which is heated while flowing down. Also in the tower technology, we can use thermal storage quite well. For example, we can use a molten salt storage, either 2-tank storages or 1-tank thermoclines. We could use fixed beds with direct contact heat exchange, for example, air rock or air ceramic pebbles. We can use fixed bed with tubular heat exchanger, for example, a concrete storage with tubes. We can use the presented moving beds, for example, particles, which work with tubular heat exchanger or work with direct contact heat exchange. And we can use phase change materials, for example, for steam processes. And last but not least, in our solar tower, we have got a conventional power block. The state-of-the-art turbines are superheated steam turbines or gas turbines, for example, recuperated ones, combined cycles, or combined heat and power, for example, with micro gas turbines. But also, the progress in material development increases temperature and pressures of steam turbines up to the supercritical and ultra-supercritical regions. So there are interesting cycles for the future. Here you see in a graph from Alstom that over time that the parameters increased steadily, and that nowadays we have about 700 degrees C steam conditions, 375 bars. And also Bugge reports this graph, and we see that in 2010 we are about 50% efficiency with our steam stroke turbines. And also in future there is still potential for development for high efficient turbines. Also, as we don't use oxygen for burning, we can think over closed Brayton cycles, which have some efficiency advantages. Here we are at the end of the presentation. I want to thank you for your attention and my DLR colleagues who contributed to the material shown here. I also want to acknowledge the German Federal Foreign Office for funding of the INAMENA project. Thank you.